In this segment, I want to talk a little bit about a word that you've used a lot in your everyday life, but maybe you've never quite spent much time thinking about what does that word mean. Here I have a meat thermometer from my kitchen, and on here it's marked in the temperature in Celsius and in Fahrenheit. And I know by looking at this that my chicken is done when it gets to 145 degrees. 145 degrees, that's when my chicken's done. What does that mean? 145 degrees, what is temperature? What am I measuring when I measure that my chicken is at 145 degrees? What is that thing that I'm measuring? What does that mean? Well, it turns out that when you're measuring the temperature of something, what you're doing is you're measuring the average kinetic energy of the molecules that make up that substance. So my chicken is good to eat when the average kinetic energy of the molecules that make up my chicken is high enough that this thing reads 145 degrees. So, temperature is a kind of a goofy thing. Let's look at this PowerPoint here. Temperature is a measure of the average translational kinetic energy of the molecules of a substance. Now, we've learned a little bit about rotational kinetic energy. I haven't dwelled on it, and I won't. But that's a thing, right? Rotational kinetic energy is also a thing. It turns out the molecules can be spinning. They have energy. That's thermal energy, but temperature doesn't measure it. Temperature measures the average translational kinetic energy of the molecules of a substance. What are our units? Well, Celsius, Fahrenheit, and Kelvin. Kelvin is our official SI unit of temperature. We will often use Celsius. Fahrenheit, that's what we're stuck with here in the United States. We will stay away from measurements in Fahrenheit. You know, it's interesting, though, to think about this, right? Let's look at this temperature, or definition of temperature. It's a measure of the average translational kinetic energy of the molecules of a substance. Okay, so you and I are sophisticated 2020-something humans, and we know that my chicken is made of molecules, and those molecules are made of atoms, but how old is that idea? How old is the atomic theory? Since this is on YouTube, that is clearly a rhetorical question. The atomic theory came into its own right around the turn of the century, between the 1800s and the 1900s, so the beginning of the 20th century, years ago. But how long have people been measuring temperature? Well, a lot longer than that, certainly. And so it's really interesting that we have this modern definition of temperature, but it's something that's been measured for a long time. So in the 1800s, the definition of temperature, and it still works, is it's the thing that is equal when heat stops flowing between two objects. Yeah, it's not a very satisfying definition. But it is still a valid definition for temperature. And this is the temperature that, or this is the definition for temperature that we would have used if I was teaching this class before the atomic theory in 1850 or something. Okay? So it is the thing that is equal when heat stops flowing between two objects. Okay, well, then we have to decide what heat is. We haven't defined heat yet, really. So temperature is a measure of the average translational kinetic energy of the molecules that make up a substance. But heat is the flow of thermal energy. So recall when we very first started talking about energy, we talked about a system, how we can define a system as the collection of interacting objects. And we said we can add energy to that system with pushes and pulls, with forces. We said we can add energy to the system with forces, and we called that work. So we can do work on a system to add energy to it. But we can also add heat to a system to change its energy. So heat and work are what we call transfer variables. So I can do work on the ball to give it potential energy. It has potential energy. It does not have work. Work is a transfer variable. A ball cannot have work. I can do work on it to give it potential energy. I can do work on it to give it kinetic energy, right? But it cannot have work. Similarly, an object does not have heat, right? I can put my lighter under this ball, and I can add some heat to it, which will increase its thermal energy. It has thermal energy. It does not have heat. Heat is a transfer variable. I add heat to the ball to give it thermal energy. So heat is thermal energy on the move. It's how we move energy into or out of a system if it's thermal energy that we're talking about. And since it's just energy, the unit is the joule, just like all of this energy business. And this is a really interesting point right here. Heat will never spontaneously flow from a colder object to a hotter object. So this is just I'm just kind of throwing this out here. This is actually related to the idea of entropy in a way that will kind of bring it back together at the end of this chapter. So heat will never spontaneously flow from a colder object to a hotter object. And maybe that doesn't seem very profound to you right now, but it kind of is, actually. And this has some ramifications for all kinds of things in physics. But, this is saying, like, now, if I go stand out in the sunshine, I'm always going to warm up, right? In other words, the sun is way hotter than I am. And so heat energy will always flow spontaneously from the sun to me. Never the other way around, right? I'm not going to walk out there one day and the sun's going to get a little hotter and I'm going to get a little cooler, right? It's not going to happen, right? So this says heat will never spontaneously flow from a colder object to a hotter object. However, we can move heat from a cold object to a hot object. We just have to put energy in order to do it. In fact, that's what your refrigerator does. Your refrigerator removes thermal energy from the inside of your refrigerator and puts it on the outside of your refrigerator. It pumps heat from the inside to the outside, from cold to hot. So we can move heat from cold to hot, but we have to have some energy input. Again, this has some ramifications for entropy that we'll circle back around, and we'll hit this again at the end of the chapter. Okay, so I think in everyday life, people will use heat and temperature somewhat synonymously, but they're not. There really are very different ideas in physics. And I guess another point that I'd like to make is that cold is not a thing, right? Cold is, it's a thing for humans, right? Humans can certainly perceive something as cold, right? But if I touch something and I perceive it as cold, then what I'm perceiving is heat flowing from me into that object, right? So, if I put my hand on this chalkboard, it feels slightly cool to the touch. Well, that's because I am warmer than it is. And so when I perceive that as cool to the touch, what I'm perceiving is heat flowing from me into it, right? So again, it's not cold flowing from it into me, right? Cold is the opposite of heat, but cold itself is not a thing, right? We move heat from the inside of our freezer to the kitchen, right? We don't move cold into our freezer. So cold is not a thing. Heat is a thing. Thermal energy is a thing. If I want to lower the temperature of something, I should remove some thermal energy. It's a tiny bit more complicated than that when you talk about phase changes and things, but we'll get to that in the next chapter. Okay, so cold is not a thing, right? When I touch something and I feel cold, what I'm really feeling is heat flowing out of me and into the object. But the opposite is true too. If I touch something and I feel that it's hot, it's actually energy flowing into my body that I'm perceiving, right? It's that heat energy flowing into my body. And so it's interesting that our perception of hot and cold has to do with what direction heat is flowing, as opposed to actually what the temperature of something is. And if you don't believe me, then look around whatever room you're in right now and touch something that is made of paper or cardboard. I've got this cardboard box. If I touch this, it does not feel very cool to me at all. It just feels, about the same. It doesn't really feel warm or cold to me. However, find a piece of metal, right? So I've got this clipboard, it's got a little piece of metal right here. And now touch that piece of metal. To me, this feels cool to me. This feels very cool, whereas this cardboard box or even this particle board that the clipboard is made of, that does not feel cool. When I touch the metal, it does feel cool. Why? Is the metal really colder than the particle board? No, these both just been sitting in my basement for like the last 6 months. They're absolutely at the same temperature. There's no doubt that this metal clip and that this particle board are at the exact same temperature. Yet, when I put my hand here, it feels not cold, and when I put it here, it feels cold. So what am I really perceiving? I'm not really perceiving the temperature. What I'm perceiving is heat flow. It turns out that this is a good insulator, and this is a good conductor of heat. So when I touch the metal, heat flows out of my body and into the metal. I perceive it as cold. When I touch the particle board, it's not as good of a conductor of heat. And heat does not flow out of my body as well. And so I do not perceive it as cold. So when you say, oh, that feels cold, you don't really mean that. What you really mean is, ooh, I feel heat flowing out of my body and into that object. Kind of an interesting thing to think about. Okay, so this brings up the ideal gas model. The ideal gas model is linked to the atomic model. So the atomic model, again, is this idea that atoms are the basic building blocks of all the stuff around us. And you've learned about that in another science class. Certainly, we'll talk a bit more about atoms as the building blocks of everything around us in the next chapter. So whatever these particles are, atoms, maybe they join together as molecules, right? The air that I'm breathing is an O2 molecule. Whatever it is that make up the particles of a gas, right? Like the air in this room. Well, whatever those are, we're going to imagine those as just little balls, and the only way they interact is bouncing off of each other. So these little balls bounce off of each other, and here we see a container of some gas, and we're imagining these gas molecules as little balls that are flying around in this container. And when I add heat, they move faster. Again, think about conservation of energy. Heat is flow of energy into the system. So we're adding energy to the system. Where does that energy go? It goes into the kinetic energy of the particles that make up the system. I add some heat, it makes the particles move faster. It's just conservation of energy, right? I add energy to the system so the particles get more kinetic energy. How do I observe that? The temperature increases. Okay. So this is the ideal gas model of temperature. The idea that temperature is a measure of the average kinetic energy of the molecules that make up a substance. So, like I said, different ways to measure temperature. We're kind of stuck with Fahrenheit in this country, not because it's a great scale, just for historical reasons. I believe that the Fahrenheit scale was made by Mr. Fahrenheit, who made body temperature as 100 and boiling water as 200. So he made body temperature 100, he made boiling water 200, and split it up into equal intervals, and that's how he created the Fahrenheit scale. Now, he was wrong about both of those values, about both body temperature and boiling temperature of water, so we're off a little bit. It's sort of a goofy scale. Again, we're stuck with it for historical reasons. Now, Celsius is based a little bit more in science. We make exactly 0 the freezing temperature of water, and exactly 100 degrees the boiling temperature of water. And then we split it into degrees, equal degrees from there. Notice that neither one of these are absolute, right? What is 0? It's just some random point, right? 0 Celsius is just some random point. We decided it's the freezing temperature of water. Could we have made it the boiling temperature of water? Sure, we just live in a universe of negative temperatures. No big deal. Works out just fine. So it's totally arbitrary, and that's kind of why we include these degrees, right? It's just arbitrary intervals between two arbitrary points. And both of these are like that. 0 degrees Fahrenheit is just a super random number, right? Like nothing interesting happens at 0 degrees Fahrenheit. That's super random. Kelvin is our official SI unit of temperature. And it does have, its scale is based on something physical. We say that 0 is absolute 0. Notice it doesn't have a degree with it, right? Because this is not just equally splitting up intervals between two arbitrary points. No, 0 is absolute 0, and 0 Kelvin means something. It means something very big. Absolute 0, or 0 Kelvin, is the temperature where all molecular motion ceases, right? So remember, we've defined temperature as a measure of the average translational kinetic energy of the molecules that make up a substance. Well, okay, what if those molecules have no kinetic energy? That's what we call absolute 0. So you can see that the absolute 0 has some very important physical meaning. It's not just arbitrary the way that the scales of Fahrenheit and Celsius are based. So absolute 0 is where all molecular motion ceases, and you can't have less than no motion. So absolute 0 is the coldest temperature that one can possibly have. It is about negative 273 Celsius. And so that makes 273 Kelvin is the freezing temperature of water, and 373 Kelvin is the boiling temperature of water. In your in your chemistry class, you probably have a couple more decimal places on here, but 3 significant figures is plenty for this class, everything we do. Okay, we can convert from one to the other. You should know that these exist. I am not going to ask you to do a bunch of conversions between Celsius and Fahrenheit. To me, that's not a very interesting problem. It's just bookkeeping more than physics. So we're not super interested in that. Celsius to Kelvin, well, that's pretty straightforward, and you will need to know that. So I will ask you to convert between Celsius and Kelvin. And the way we get that is we just add or subtract 273. If I have Celsius, I add 273 to get Kelvin. If I've got Kelvin, I subtract 273 to get Celsius. And this is an important point to remember. Anytime we have a delta T, and we will often talk about delta T's, it's often the change in temperature that is physically significant, and not the temperature itself. So the size of a Kelvin is exactly the same as a size of a Celsius degree. So that means that if an object's temperature increased by 10 degrees Celsius, then it also increased by 10 Kelvin. Its final temperature will have a different number in Celsius and Kelvin, but the change is exactly the same because those degrees are exactly the same size. Whereas the size of a Celsius degree and the size of a Fahrenheit degree are not the same. A Celsius degree is bigger. In fact, it is 9/5 of a Fahrenheit degree. So almost twice a Fahrenheit degree. About 1.8 times a Fahrenheit degree is 1 degree Celsius. But again, I'm not going to ask you to do a bunch of conversions there. But you should know that there is an equation. You can do it if you need to.